Okay, here's another example of redox reaction split into its two half reactions. So this is the answer that I'm trying to get to. So if I have zinc positive ions going to positive zinc positive, tin positive 2 going to tin positive 4, and iron positive 3 going to iron positive 2, what happens? Well, the zinc positive 2 loses 2 electrons to form the positive 4, and the Fe positive 3 gains 1 electron to form the Fe positive 2. And so, in order for the oxidation reduction to occur, there has to be an equal exchange of electrons. So, the number of electrons here that are released must be the number that are taken in here. So, that's why I multiply everything through by 2, my ion there and my ion here. And of course, the electrons. But then they cancel out in the final equation. So the reaction, the overall reaction, looks like this. And I'm just leaving out any anions that would be involved in this reaction because they're not important when you're talking about just the oxidation reduction part. It's really just about the species that are losing or gaining electrons. And then I've identified up here which one's oxidation, which one's reduction. Okay, and then I'm going to go through this one example with you down here, which is one where again it's just the reacting species that are involved. The positive ion in this case is taken out. So in the first one, the two components that would be involved in the first half reaction, I always say they look like they're in some way related, and they can have, they'll have some similar component to that. So the first one, I have MnO4 going to Mn positive 2, and what's happening here? Well, first of all, I see I have one Mn and one Mn, so no coefficient needed there. Then I see I have 4 oxygens here. The only way to balance oxygen is with water molecules because the reaction's occurring in water, you can use water to balance the equation. And so I would add 4 water molecules to balance out the 4 oxygens here. When I do that, I end up throwing hydrogen into the mix. And so I have 8 hydrogen ions here, 4 times 2. And so I would put the hydrogen ions over here. So then the next thing that I would do, I would go through and I would balance by charge. So I see that I have from the 8 hydrogens, I have positive 8 here. I have a negative 1 here, and I have a negative 5 here. So overall, I have a positive 2 on this side. And then I look here, and only the Mn positive 2 contributes charge on the product side. So I have positive 2 here. So this reaction is balanced according to charge. So now I do the next half reaction. The next one, I have C2O4 negative 2. And so what's happening here? Well, the first thing I have to do is I have to balance the carbon with a coefficient. I put a 2 out in front. When I do that, I have 4 oxygens. I have 4 oxygens here. I don't have to use water in this reaction at all. That was a mistake. Okay, so now what I do is I look at the charge and I have the balance by charge. There's a negative 2 on this side. I have no charge on this side. So I make this side have a negative 2 because they have to balance out by charge. And the way that I got my 5 electrons here, sorry, I'm backstepping. The way I got my 5 electrons here The only way I could make both of these sides have the same charge of positive 2 would be by adding these 5 electrons. So initially I had a positive 8 and a negative 1, which is a positive 7. And the only way I could get this side to have a positive 2 like this side was by adding these 5 electrons. Okay, you do that step before you do your check. All right, so now I need to balance the electrons to be the same in both equations, because this one has 5, this one has 2 down here. So I would multiply this whole equation through by 2, and I would multiply this whole equation through by 5. So when I do that, what I end up with is, I'm going to go through and balance it all out for you. I'd end up with 16 hydrogens. I'd end up with 2 of the MnO4 -1. I'd end up with 10 electrons, and then I would end up with 2 Mn +2 and 8 H2O. Okay, so you have to go all the way through with it. And then in the other equation, I would have 5 C2O4 -2, and that would go to 10 CO2 plus 10 electrons. All right, so now I have, as long as I have 10 electrons on opposite sides, I'm probably in good shape. So I can see that my electrons cancel. And sometimes you'd have water in both equations and you could cancel some out, but we don't. So I won't do anything with the water except for add it into my final reaction. And so my final reaction is going to look like this. It's going to be, it's going to have 16 hydrogens plus 2 MnO4 negative plus 5 C2O4 -2. And on the other side, so I'm just pulling everything down, 2 Mn +2 plus 10 CO2 plus 8 H2O. And now if I check my charges, check everything in according to charge, sorry, you're going to have to ignore my example right there. I'm going to see I have a positive 16 here. I have a -2 here. I have a positive 10 here. And then on the other side, all I have is positive 4. 2 times positive 2. No charges on either of those. So now what I see is that I have a positive, sorry, I have a -10 here. 5 times -2, I quickly looked and said that math's not going to work. So I have 5 times -2 is -10. So I have -12 here, -2 and -10, and a plus 16, which equals a plus 4. So if the reactant side and the product side in the end has the same charge, then you probably did your redox reaction correctly. And then you can go through and check and identify all the species and make sure it works as well. I think I'll stop there.